Hello, everyone. In this video, we will study series and convergence. Series. An infinite series is the summation of the terms of an infinite sequence. That is, an infinite series is a sum with infinite number of addends. The nth partial sum is the sum of the first n terms of a sequence. That is, Sn is the sum from the first term to the nth term. Use a new index I to enumerate from the first term up to the nth term. Let sequence S be the sequence of partial sums. That is, the nth term of sequence S is the nth partial sum of sequence A. If the sequence of partial sums converges, then it means that the limit of the partial sums exists, and the series is convergent. S is called the sum of the series. If the sequence of partial sums diverges, its limit does not exist and the series is divergent, and the series has no sum. Example 1. Find the third partial sum, the sixth partial sum, and the ninth partial sum of the series. Solution. A. The third partial sum is the sum of the first three terms of the series. Therefore, the third partial sum is equal to 49 over 36. B. The sixth partial sum is the sum of the first six terms of the series. Thus, the sixth partial sum is approximately equal to 1.49. C. The ninth partial sum is the sum of the first 9 terms of the series. Hence, the ninth partial sum is approximately equal to 1.54. Example 2. Find the nth partial sum and the sum of the series. Solution. A. The nth partial sum is the summation of the first n terms of the series. Simplify each term of the series. To find a formula for the partial sum, try to reduce the number of terms to get a closed-form formula. Multiply the partial sum by r, and subtract the product from the original partial sum. Distribute r. Notice that most of the terms get cancelled. And only the first and last terms remain. Solve for the nth partial sum. Therefore, the nth partial sum of the series is given by the following formula. B. The sum of the series is the limit of the partial sums. Apply properties of limits of a sequence. Recall that an exponential sequence converges to 0 if the absolute value of the base is less than 1. Which means the series has a sum only when the base satisfies this inequality. Therefore, the sum of the series is given by this formula. These formulas for partial sum and sum of the series apply to geometric series. Example 3. Find the nth partial sum and the sum of the series. Solution. A. The nth partial sum is the summation of the first n terms of the series. Simplify the partial sum. Thus, the nth partial sum is equal to the first term minus the last term. This series is called a telescoping series where terms are cancelled by other terms in the series. B. The sum of the series is the limit of the partial sums. Apply properties of limits of a sequence. And a limit at infinity expression. Hence, the sum of the series is equal to the first term. Geometric series. A geometric series has the form: the summation of a constant times another constant raised to n-1, from n equals 1 to positive infinity. A and r are constants, where a is not 0. The nth partial sum is given by the following closed-form formula. It means that we can compute a partial sum of a geometric series using this formula without the need to enumerate the n terms of the partial sum. The convergence of a geometric series, or whether the series has a sum or none, depends on the value of r. The geometric series is convergent if the absolute value of r is less than 1. That is, if r is between -1 and 1, the series converges. The sum of a convergent geometric series is given by the following formula. The sum is equal to the constant multiplier divided by the 1 minus the constant base. Meanwhile, the geometric series is divergent if the absolute value of r is greater than or equal to 1. That is, if r is less than or equal to -1 or r is greater than or equal to 1, the series diverges. The sum of a divergent series does not exist. Example: determine the convergence of the following series. Solution. A. Write the series as a geometric series. Use properties of exponents. The series is a geometric series where a is 1/2 and r is 2/3. Because the absolute value of r is less than 1, the geometric series is convergent. B. Write the series as a geometric series. Use properties of exponents. The series is a geometric series where a is 1 and r is 1 over the square root of 5. Because the absolute value of R is less than 1, the geometric series is convergent. C. Write the series as a geometric series. Use properties of exponents. The series is a geometric series where A is 8 and R is B over 8. The geometric series is convergent if the absolute value of R is less than 1. Which also means R is between -1 and 1. Therefore, the series is convergent if B is between -8 and 8. And divergent otherwise. P-series and harmonic series. A P-series, where P is a constant greater than 0, has the form the summation of 1 over n raised to p, from n equals 1 to positive infinity. It is also called the hyperharmonic series. A P-series is convergent if P is greater than 1. These are examples of convergent P-series. Meanwhile, a P-series is divergent if P is less than or equal to 1. These are examples of divergent P-series. The harmonic series is a P-series for P equals 1. Because P equals 1, the harmonic series is divergent and has no sum. Example. Determine the convergence of the following series. Solution. A. Write the series as a P-series. Let m equals n-3. When n equals 4, m is equal to 1. The series is now a P-series with P equals 2 over 3. Because P is less than 1, the P-series diverges and has no sum. B. Write the series as a P-series. Factor the denominator and divide out a common factor. The series is now a P-series with P equals 1, which is a harmonic series. Because P is equal to 1, the P-series diverges and has no sum. That is, the harmonic series is divergent. C. Write the series as a P-series. Divide each term in the numerator by the single-term denominator. Apply a property of exponents. The series is now a sum of two P-series with P equals 3 and P equals 4. Each P is greater than 1, thus each series converges, which means each series has a sum. Therefore, the sum of these two series exist, and the sum of the two series converges. Telescoping series. A telescoping series is of the form the summation of the nth term minus the next term, from n equals 1 to positive infinity. The terms get cancelled eventually by terms down the series. A telescoping series is convergent if the terms converge to a number L that is, the terms of the series become closer and closer to L. The sum of the series is equal to the first term minus the limit of the terms. Note that of the 1st of May represent the terms that don't get cancelled, and not just the first term of the series. Example 1. Determine the convergence, the nth partial sum, and the sum of the series. Solution. A. Write the series as a telescoping series. Take the limit of the terms of the series. Refer to the following limit at infinity expression, which means the terms of the series converge to zero. Therefore, the telescoping series is convergent. B. The nth partial sum is the summation of the first n terms of the series. For each n, let's call the first term as the minuend and the second term as the subtrahend. Write the terms of the partial sums. And then write out terms that cancel each other. We don't see a clear pattern yet, so we proceed with writing the next batch of partial sums. Write the terms of the partial sums. And then write out terms that cancel each other. Now, we see a pattern of the partial sum as n becomes larger. Notice that the terms that remain are the minuend of the first three terms and the subtrahend of the last three terms. Then, let's write the partial sum in terms of n. The remaining minuends are the same, while the remaining subtrahends have denominators that are greater than the value of n by 1, 2, and 3. Therefore, the partial sum is given by the following formula. C. The sum of the series is the limit of the partial sums. Substitute the expression of the partial sum, and then evaluate the limit. Use a limit at infinity expression. Thus, the sum of the series is equal to -11/6. This means that the sum of the series converges to -11/6. As the number of terms of a partial sum increases. Example 2. Determine the convergence, the nth partial sum, and the sum of the series. Solution. A. Take the limit of the terms of the series. Let m equals 2n-1. As n approaches positive infinity, m also approaches positive infinity. Recall a limit at infinity expression of an exponential function. The terms of the series converge to zero. Therefore, the telescoping series is convergent. B. The nth partial sum is the summation of the first n terms of the series. Write the first few terms of the partial sum. and then write out terms that cancel each other. We see a pattern of the partial sum as n becomes larger. Everything is cancelled out except the terms at the start and the end of the partial series. Therefore, the partial sum is given by the following formula. C. The sum of the series is the limit of the partial sums. Substitute the expression of the partial sum, and then evaluate the limit. Use a limit at infinity expression. Thus, the sum of the series is equal to 1 over e. This means that the sum of the series converges to 1 over e, as the number of terms of a partial sum increases. Alternating series. It has terms that are alternately positive and negative. It can be written in any of these form as a product of a power of -1 and the absolute term, where the absolute term is greater than 0. An alternating series is convergent if the absolute terms are decreasing for all n. And the absolute terms converge to 0. Example 1. Determine if the series converges. Solution. Write the series as an alternating series at multiples of pi over 2. Recall that the sine function alternates between +1 and -1, where the value of n for each term is as follows. As a consequence, the given sine function can be written as the following piecewise function, and as powers of -1, which leads to +1 if the exponent is 0 or even, or -1 if the exponent is odd. It follows that the series is equivalent to this alternating series. The sequence e raised to -n is decreasing for all n. Because it is sample values of a decreasing function e raised to -x. Recall a limit at infinity expression of an exponential function, which means the sequence e raised to -n converges to 0. Because both conditions are satisfied, the alternating series is convergent. Example 2. Determine if the series converges. Solution. The sequence n raised to 3 over 4 is not decreasing for all n, because it is sample values of an increasing function x raised to 3 over 4. Recall the following limit at infinity expression, which means the sequence n raised to 3 over 4 does not converge to 0, rather it diverges to positive infinity. Because at least one of the conditions is not satisfied, the alternating series is divergent. Properties of convergent series. Suppose two series are convergent. Let K be a constant. The following combination of series are also convergent. The constant multiple of a convergent series. The sum or difference of two convergent series. The convergence or divergence of a series is not affected by deleting a finite number of its terms. That is, a series from n equal to 1 to positive infinity, and the same series in which the terms before capital Nth term have not been included. Either both converge or both diverge. Example 1. Determine if the series is convergent or divergent. Solution. Write the series as a sum of series with known convergence or divergence. Use properties of exponents and fractions. The first series is a convergent geometric series because r is less than 1. While the second series is a divergent p-series because p is less than or equal to 1. Because one of the series is divergent, the sum of the two series is divergent. Example 2. Determine if the series is convergent or divergent. Solution. Write the series as a sum of series with known convergence or divergence. Use properties of exponents and fractions. The first series is a divergent geometric series because r is greater than or equal to 1. While the second series is a convergent geometric series because r is less than 1. Because one of the series is divergent, the difference of the two series is divergent. Example 3. Determine if the series is convergent or divergent. Solution. Write the series as a sum of series with known convergence or divergence. Use a property of exponents and partial fraction decomposition. The first series is a convergent geometric series because r is less than 1. The second series is a convergent telescoping series because the terms of the series converge to a limit, which is equal to 0 in this case. Because both series are convergent, the sum of the series is convergent. Convergence of a series. So far, we have learned that a convergent series has a finite sum. In terms of the limit of the terms, if a series is convergent, it follows that the terms of the series converge to 0. However, the converse of the statement above is not always true. That is, if the limit of the terms is 0, it does not necessarily mean that the series is convergent. Meanwhile, a series can be either convergent or divergent if the limit of the terms is equal to 0. That would mean that another test must be performed in order to figure out the convergence of the series. These convergence tests are discussed in the next videos. Consequently, we can only test for divergence using the limit of the terms. If the limit of the terms is not 0 or does not exist, the series is divergent. Example. Find the limit of the terms of the following series. Solution. A. We found out earlier that this geometric series converges, because r is less than 1. Take the limit of the general term. Recall that an exponential sequence converges to 0 if the absolute value of the base is less than 1. The limit is 0, which means the terms of the series converge to 0. B. We found out earlier that this geometric series diverges, because r is greater than or equal to 1. Take the limit of the general term. Recall a limit at infinity expression for an exponential sequence. Thus, the limit does not exist and is positive infinity, which means the terms of the series diverge to positive infinity. C. We found out earlier that this p-series diverges, because p is less than or equal to 1. Take the limit of the general term. Recall a limit at infinity expression for a rational power greater than 0. Thus, the limit is 0, which means the terms of the series converge to 0. This example demonstrates that if the terms of the series converge to 0, the series may still diverge, which means the series does not have a sum, even if the terms eventually become 0. Now, let us conclude with the statements about the convergence of a series we learned earlier. If the series is convergent, it means that the terms converge to 0, as shown in Part A. But if the series is divergent, the limit of the terms can be non-zero, does not exist, as shown in Part B, or 0 as shown in Part C. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.